Well, shall we begin? I'm to talk about applications of computers. Now, you probably already have understood that this course is a large number of anecdotes from my experience about how science and engineering runs. And in fact, that is what the course amounts to. It amounts to all the things I think you ought to know about, but is not taught in a normal course. This one begins with a story that about mid-50s, something like that, I discovered I was extremely nervous addressing large audiences. Now, I taught in college, so I was used to talking, but big audiences frightened me. Now, a function of a scientist is to communicate. There are written books and written articles. There are formal talks, and there are informal, quick talks. You should master all three. If you're going to create something, there is an obligation on your part to communicate. A large number of people don't do this. I felt the necessity, so I said I'd do something about it. Now let me first talk about the informal talks. I have quite a few of my friends at Bell Labs who are what I call backroom scientists. They're invited to a conference. We're going to make a decision about whether we're going to build it this way or that way. We make the decision, we go ahead. 2 weeks later, they issue a memorandum about why we should have done something else. It would be desirable for them to stand at that moment and say, you are doing it wrong for these reasons, bing, 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 bing. This ability to talk at the drop of a hat and give a very good, clear explanation is very necessary in this age of group activities. When a committee is meeting or something, you have got to be able to speak up promptly and to the point and carry conviction. Now, the other ones were a little more troublesome, particularly the large speech. I said, well, you got to do something about it, Hammond. You cannot become a great scientist if you cannot communicate well. It's one of the necessary things. So I said, I've got to learn. I've got to practice. I have to accept giving talks, even if I don't like to. Well, shortly afterwards, I was asked from somebody from IBM if I would give a talk one night in New York to a group who were studying. Now, I knew what that was because what they normally do is they get a bunch of people, say people who are learning a new machine or something, and they assemble them in New York. Monday night, they have a get-together party. Tuesday night, maybe they give them tickets to a theater. Thursday night, maybe they have a lecture or something. But they have a problem of entertaining the people for 4 nights in New York. And one of the things is kind of a talk on computers. Well, I didn't know exactly what it was, but I wanted to give a talk so good that I'd be asked to give it again so I get more practice. Well, the first thing you think you're going to do in those circumstances is talk something you are very, very interested in and you are expert in. That's not the way to get invited again. You'd better start asking what is it they want to hear. Now, I'm not talking entertainment. I have a friend in computing who spent so much of his time being entertaining, he was gradually pushed out of the computing field. I am talking about communicating, but on topics other people want to hear. So I thought for a long while, now this is in the 50s, and I came up with the title, The History of Computing to the Year 2000. It was going to be interesting to me. Now, it furthermore had the feature, which I point out to you. It meant that as years went on, and I gave the talk again and again and again, I had always to keep track of what was happening and look at what the new things that might be possible. It kept me acutely aware of the future possibilities of computing. It kept my attention on that matter. It was just the kind of a thing I should do. And it's one of the things I want to summarize this point. When you give talks, when possible, you should profit by it also. It worked out very well. I gave the talk. They said it liked very well. And I said, well, I'll be glad to come in and do it again. And sure enough, I used to go in about 3 times a year for maybe 6 or 8 years and give such talks. I got all the practice I wanted. But you see, it also did this other thing for me. When I use the expression frequently, luck favors the prepared mind, which is a remark of Pasteur, and I believe in, you see, in some extent, I was making my luck. I thought about what was wanted. Now, the first time I gave the talk was on computers. I turned up, which is really the talk 2 times ago, except I had gorgeously prepared slides with curves for noise and curves for the uncertainty of quantum principles and such other things. Beautifully done. Very convincing. But you notice I didn't use them to you. I finally found out saying, come on, think about the size of molecules. Think about impurities. Think about how fast velocity of light goes. Think about heat. And you see the nature of the problem without any elaborate quantum mechanical curves, which you probably didn't understand anyhow. I reduced it down to things you could understand. Well, I gave a talk a couple of times, and I began to realize that the future was not limited by the machines, it was limited by the software. So I started giving a talk on hardware and software. But after a while, I came to the realization that while not completely true, a great deal depends upon economics. What applications? That was going to control the development of machines. So I had to do this third talk. So the talk gradually moved from 1 to 3 different things. All because I said to myself, I have to learn to be able to give public talks. Well, now computing began as simple arithmetic. At Los Alamos, we were just grinding out numbers for atomic bomb design. Just numbers, 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 and there was only one letter. We named the designs by letters of the alphabet. So there was a letter P on the problems, all those cards involved with problem P. There was a Q on all those, but outside that it was all numbers. And this was generally how you think about it. But if you go back to something like 1300, there was a guy named Raymond Lull, or Lully, which is the way you want to spell it. He lived on Minorca. He was a Franciscan, I think. And he had the idea of building a logic machine. It's a screwy idea. Now, if you will read, as you probably have, Swift's Gulliver's Travels, what you possibly don't know, that it's a tremendous parody on everything. The people who break their eggs at one end or the other were one of the political parties or the other political party. The whole business of the island of Laputa is exactly a spoof on Lull. Raymond Lull's idea is that you could build a machine which would do thinking for you. So it does go very far back. 1300 was probably about the middle of his life, and it isn't the first time. On the other hand, we began by number crunching, pure and simple, because they were the only people who could afford the bill. Machines were expensive, and there was no other way of doing it. As machines became cheaper, we started doing other things. Now you see word processor. Now when I see a personal computer in somebody's office sitting idle, I cannot help but think, my God, if we'd had that back then, what computing I could have done with all that idle time. Machines that come so cheap, they're like telephones. They're idle most of the time, right? In the early days, no. My bosses used to want to know what fraction of time I was running. I was up sometimes to 97% efficiency throughout the week. And I argued with them, look, that's not the way to run computing. It's machine efficient but human inefficient. I pointed at the telephone and I got brushed off on that one, so I made another study. I studied men's johns. And I came to one conference and said, I've made a study of men's johns, and there's always some capacity for somebody. I have never seen a john which there was not some capacity. You put in sufficient capacity so that people don't have to wait. Don't you think you do the same for computing? It's pretty much the same stuff. They argued that it was a legal requirement, but I got the point across that it was foolish to have machines work close to maximum efficiency. It's tremendously inefficient for the humans. And we've gotten now down to almost the opposite. Personal computers operate a very low fraction of the time, and they sit idle waiting for you. So we got some progress there. And we shifted around. Now I want to tell you another aspect of the problem which you will meet in varying forms. At Los Alamos, we were solving a large partial differential equation on relays. When I went to Bell Labs, one of the first problems I solved on the relay computers for Aberdeen was a big problem, partial differential equation on design of relays. I actually solved a partial differential integral equation on our accounting department equipment. In short, I did very difficult problems on relay computers. When we got better computers, I was reduced to doing trajectories of guided missiles, trajectories to the moon, and such other things, which are ordinary differential equations and are much easier. Some years later, I wrote a couple papers on trajectories. I wrote a couple papers on just how to integrate. Then I wrote a paper on how do you evaluate a function. And finally, I wrote a classic paper on how do numbers actually combine. With the most difficult equipment, with the most primitive equipment, I was asked to do the most difficult jobs. At the back end, with the very advanced equipment, I was doing simple jobs. Now, this is what happens to any new idea. If you have a new idea which is going to influence your organization, you're going to have to demonstrate it will work under the most difficult conditions, the worst possible ones. When you finally get it installed, the bulk of the time be spent on much simpler ones. But somehow or other, there's a very, very big impedance that people demand that you be able to do the worst, most difficult things first. Then you get around to do the ones you want to do or should be doing. I tell you this because on numerous occasions I've faced the thing and I've had to take action. You want to size up the opposition, and there are times when it's better to abandon the idea and go do something else. And I'll stick one more of those stories in along the way, if I remember to do it, on exactly my doing that kind of a thing. Now, very early after I got started, I realized I was in the mass production of a variable product. That's exactly how I said it. I am trying to set up the situation so I can do all of next year's proposed problems. I don't know what they're going to be, but they're going to fall in certain categories. How do I do it? And I told you with the 650, I spent 1 man year, which was really several people working parallel for maybe 4 months, to get a software system going. Within a year, I had more work done than I ever would have gotten done if I'd gone at the problem straightforward. In short, it paid me to build a software tool. But beware. The machine 650 didn't stay around more than 2.5 years before something else came along. If you try to build some software, you're going to get paid back for it. You'd better get those savings within a year or a year and a half, or you're likely not to get the savings. We are living in a changing time. These ideas don't last long. And so you've got to get your money on software. But it pays to build tools. Everybody knows it pays to take the time to build a tool, and building a software tool for the 650 greatly increased the amount of work I could do within 1 year. Now, I have ignored, much later in the lectures, I'll talk about one where I did a large business job for AT&T renting a UNIVAC in New York City. So I will do some, but fundamentally I'm concerned with engineering problems. And what I observed, time versus the log amount of operations, there was a curve research was bending over. Now, you've seen why curves bend over. There's a saturation point. 2 reasons. One is that given 1,000 scientists, just how many problems can they ask per day and still be scientists? There's a limit to how much they can ask. Now, they can ask for bigger problems, but the number of problems they can ask is quite limited. They can't absorb the answers. They can't think that much. So it curved up and started bending over. But I spread out the work gradually to engineering. After all, as part of Bell Labs, and there was a whole Bell Labs engineering part. 90% was the engineering, 10% was research. So I found a load engineering coming up like this. And remembering this is logarithm, that's a great deal larger. And we have a military location at Whippany, New Jersey, which is devoted mainly to military problems in the past. I don't know what it's doing now. And they came along like that. Now, the result was that I saw the straight line growth. After that came word processing, which, as you know, occupies an enormous amount of time. Your compiler, when you use a Fortran compiler, or your assembler, or your monitor system, are all symbol manipulating things. They're not doing any scientific computing at all. They're just throwing symbols around. And I think we'll go on and find pattern recognition as a large consumer of computing. I don't think you can solve the general pattern recognition problem because it's too difficult. But a great many pattern recognition problems will probably be done by machine. And you also find that, say, virtual reality, which requires an enormous amount of computing, will absorb a great deal of computing time, a great deal of computing power. So the curve is not over with. It's still going to go, but we are beginning to saturate von Neumann type machines and having to go to parallel processing to do it. Well, let me talk about another episode. Jack Kane. He was a guy at Bell Labs, and he was crazy in the sense that I can prove he was crazy. He was at one time more like that, and I get a letter from now and then, and I can prove to you he's crazy. But that's beside the point. He had an idea of connecting a new machine, a scientific data systems machine, to the cyclotron at Brookhaven, which we were using, to reduce data on the fly. Well, Jack was clearly crazy. And my vice president stopped me in the hall one day and said, look, he says, Kane thinks he can do these things. You know something about computers. Will you please investigate and tell me whether you think this can be done? Because it's a very novel idea at that time. So I call up Jack, and we go to lunch frequently, and I begin to find out, yes, he's crazy, but he's got good ideas. And then I look at the machine, and I report back to Vice President, yes, with some guidance from me, Jack Kane can do that job if you give him the machine. Then the Vice President said to me, I don't want to get a machine from fly-by-night company. We'll be gone next week. Are those people likely to stay in business? That's not in my field of mathematics, mind you, but it's a question which he asks, I must answer, right? It happens that I know slightly the president. And so, having first studied the question, gone to IBM and asked a lot of pointed questions about their manufacturing and so on, and studied some books in economics, I make an appointment with Max Palevsky saying, I would like to meet you out in your office at such a date about 10 o'clock. I want to talk about your company and we getting a machine because there's some doubt that the company will be in business long. So I walk into his office, we are polite, and then I say to him pointedly, right out, the major cause for failures in this business is not enough capital. Have you got enough money? He laid it out beautifully. I asked him one of the pointed questions. He answers beautifully. We walked down the production line. I inspected, having looked at IBM and some other ones, and it looked good. So I reported back, yep, we could. We got the machine, and with some guidance from me, Jack installed it, and by God, it was working great. Well, comes now another part. We are also using a Van de Graaff at Rutgers, which is pretty much the same AI particle accelerator, and we want to put a machine on that. Well, we had originally gotten the smallest machine which would do the job, and of course, when you get the smallest machine, we had had a lot of trouble making it work. I thought we'd entitled somewhat better machine, and this time is in the matter of hands not of the vice president, but in heads of a department head who's in charge of that kind of stuff. And I'm in his office one day, and I say, well, when are you going to make up your mind about getting him which machine? And he says to me, I'm going to decide when all the department is agreed which machine. I looked up at him and said, you mean you're going to settle for the stupidest mind of the bunch? And I walked out and never went back. Now, I had a lovely job at Bell Labs like that. I stuck my nose into business where it wasn't needed, and I walked off. Now, sometimes my boss assigned me jobs, but fundamentally, I was in that position. And when I saw the opposition was that much, I walked off. I decided there were other things I could do which were more constructive than fighting a guy who wants to settle for the stupidest mind. Now, once we did these couple, we naturally wanted to put computers in Bell Labs to laboratory work too. After all, these little small computers were just coming in, and the personal computers, which were often kits you bought and assembled for yourself, but there were a few ones which you could buy already assembled. So we started doing this to reduce the data and the various experiments right on the fly, because my arithmetic suggested that the one at Brookhaven probably doubled the capacity of the machine, because when the data was reduced on the fly, you noticed that it wasn't quite enough counts. Oh, the damn sample must not be in the middle of the beam. We cut off the power, we go in, we adjust the thing, we come back out, we hang up the keys, we turn the juice on again, and sure enough. Or there's something funny happening at the end of that spectrum, we better get some more stuff up there, we go back, slightly change the experiment, and resume. We caught runs early that were going to be no good, whereas they used to run 18 hours and then look at the data. And of course, frequently the 18 hours were wasted. That's how I think we doubled the capacity of the machine. Well, when we put these in Bell Labs being electronic heavily, there has to be, for an experiment, a bunch of electrical stimuli. And people quickly learned that if they put a digital analog thing on the end, the machine could generate the input stimuli. So we started doing that. We'd put the stimuli into stimulus, a sequence of square pulses or a square pulse followed by a sinusoid. We could put in these signals very easily. Well, once you have the signals in and the data reducing out, you're ready to close the loop and get a feedback system. Now you're in a position that's quite different. You can let the machine, while the experiment is being done, adjust itself for what you want. Now I tell this story because this is what happens with machines in the past. We got them for one reason. We promptly used them for other ones. The presence of the machine changed the job, and we could respond with general purpose machines to the changed situation. When you get special purpose machines, you cannot do that trick anywhere near as well. And I was greatly impressed at how many people got machines in and how that changed it. In fact, the whole psychology department finally got a glorious big machine in with a large number of terminals, and they only did interactive experiments. Like shining a light on a person's eyeball to watch how the iris grew, and then changing the signal and watching the frequency which the eyeball could respond to or not, trying to probe what was the feedback mechanism in the brain that controlled these things. Because if you've got the frequency response, you have some idea, if it's a linear system, what the mechanism is, what the feedback paths are, and so on. We started doing a large number of these interactive experiments, and it proved to be very, very useful. The social science department was one of the most active. Now, I want to go on to another topic along the way. The same vice president asked me, yes. He said, some people at Boeing, Seattle, are going to ask you to come out and spend 2 weeks looking at a computing center. It might be a nice thing if you went. Now, he didn't order me to go. He never did that. But I got the message, and so when they called up, I agreed. I was in for a surprise. I thought I was going out there, the guy who invited me, to inspect how well they were doing computing, managing machines. Well, the first day, Monday, he's escorting me around. Suddenly, I am sidetracked by his vice president, separated from him, taken into a room which a large number of vice presidents and some of the board of directors are there, and said, what we want to know is this guy doing a good job or not? Not how the computing there, but there. I gulped 6 times and thought about walking out, and I said, no, my vice president probably knew that was a job. He just didn't want to tell me in advance. So I'm probably doing the job he wants, so I guess I'll have to do it. Well, the first thing I found out was that Boeing kept a record of the current design of the airplane on a tape. Now you'd keep it on a disk. And the idea was very simple. We shall use that, and everybody will be compatible all the time. It didn't take me very long to find out that was not what happened. It cannot happen. Suppose you're in the wing design department. If you are trying to make small changes here, there, and yon to see if the flight is better, and if somebody over there changes something over there, you may see something better when your new design was worse, right? What you do is you make a copy of that tape, and you use that tape unchanged by anybody else until you get your design perfected, because you cannot do an optimization design if the constants you are using are constantly changing. No way. When they got it done, then they would try to integrate it with the rest of the plane. Now, I think the vice presidents thought that the tape was being used, but every group, in fact, did something quite different. They got a copy, latest one they could. They froze on that one until the finished optimization was done, and then it was integrated back in. You can see why it has to happen. Now, it brings up databases in general. Databases are a very, very difficult topic. Every damn big executive I've ever met, right, he felt that if only he had the complete state of the company at every moment, he could make better decisions. Well, let's ask the question, a brutal one. If the decision is going to depend upon moment-to-moment data, is that a decision a president or board of directors should make? They should be concerned with long-term effects, which should not depend upon moment-to-moment situations. Right? Therefore, that idea that they have that they can manage better, yes, they can micromanage better, but they really should not be making important decisions based on moment to moment. Those decisions should be made at a lower level, by far. And in some companies, they finally were. So the idea that you have a company database is not such a red-hot idea as you might think. It doesn't get too well. Now, one other feature bad, suppose you and I are both vice presidents of a company, and there's going to be a meeting Monday morning, and so you go in Friday afternoon and run the programs to get the results. And you have the graphs showing what's going to happen. But I, knowing that a great deal of data comes in over the weekends, because telephone lines are cheaper then, I go in Sunday night using exactly the same programs but a different database, and I come up with different conclusions. And we walk in the present. You have one set of curves, I have another set. It is not tolerable. It is not a reasonable way to operate a company. So the idea that I can have a rapidly changing database and use it to make high-level decisions is very, very dubious proposition. But what about scientific databases? So you have a scientific database and there's a velocity of light in it. And somebody in your organization makes a new measurement of velocity of light. He wants his in. There's